So here is our small setup for timing the pulse, which is going to travel down the cable, which you can see wrapped on this drum. There are 200 meters of cable there, and we have the ends of the cable and all bits of electronics to enable us to do some measurements. So what are the electronics? The little orange box in the front, where you see the numbers flicking around about 245, is actually measuring the frequency of the pulses which are being produced by this little grey box here. And that frequency is measured in thousands of hertz, kilohertz, and it's around about 250 kilohertz. It's 245, 0.8, 0.7, etc. So that enables us to tell us how far apart the pulses are in time. The green screen above is showing what's happening to those pulses. And if I can zoom in just a little bit, you can see what's happening. If I adjust this very slightly, you can see that we end up with a little static picture and then something which is jumping up and down in the middle. What I'd like to do is just to take away the jumping up and down bit in the middle, because that's caused by the cable, and I can do that just by switching this off at that point. No, I can't. Let's do it that way. So there we have two pulses. The screen starts, this is an oscilloscope, and I'll just show you how that works. We have something which is causing a spot to sweep across the screen, and it's being deflected up and down by the pulses. And every time I make this little clicking noise, I increase the speed with which the spot goes across the screen, and eventually, if we whip the spot across the screen fast enough, we manage to separate these pulses, which are occurring every 250,000th of a second, into separate pulses. And there we are. That's as fast as this little oscilloscope will go. And at this setting, each of the little divisions here is 1/2 of a microsecond. So between the beginning of the screen there and there is 1 microsecond, 2 microseconds, 3, 4, and a little bit microseconds for the time interval between those two pulses. If we now connect our cable to this system and just leave it to sit there, oh, lo and behold, we get a little reflection which occurs in between the two pulses which were there already. And you can see, I hope, that this pulse starts 1, 2, 3, about 3.4 divisions after the initial pulse. So we have a way of measuring, since we know that that distance is caused by our signals at 245 or so kilohertz, we now know the time interval between the start of the pulse and its reflection having travelled down the cable. Now, to take my word for it that there's 200 metres of cable, I unwrapped it and rewrapped it. It was a real pain to do so, and it was brand new cable, so we'll assume it's about 200 metres. Now, there's a couple of other bits we can do which might amuse you. If we take the ends of the cable, and perhaps I could just zoom out a little bit now so you can see what I'm doing a little bit more. Here are the ends of the cable, and at the moment they're just sitting there providing a reflection. If I touch them together, so we short the ends, you will notice that the reflection now occurs upside down. And that's the bit that causes the pulse to go upside down. So if I leave the cables unconnected, we get an upward pulse, and connected, we get a downward pulse. But it stays in the same place. That little wiggly bit stays in the same place, so it indicates that we are actually doing something with the end of the cable, and it isn't anything that I'm doing that's magic which is causing that. So if you can perhaps see it on the screen now, as I touch the cable, it moves a little bit. I'm going to zoom in a little bit more on the oscilloscope and just show you another small cheating thing that we have. Here is a little pair of boxes which have got some electrical resistors in them, and they're nothing very special. And what I'm going to do is to allow the cable now to have a particular resistance across its ends, and I'm just going to plug in the cable now, and lo and behold, the reflection just disappears. And this is the way that people design radio aerials, because what you would like is this 250 kilohertz signal just to leave the end of the cable and go off into space. And so that's what this little system is doing. By adding the resistor across there, we can do it correctly. I can show you with a rather less upmarket resistor. That's just this one. and if I just put that across the ends of the cable, this isn't quite right, so the pulse doesn't quite disappear, but as you can see it does. And if we had a radio here which was sensitive to 250 kilohertz, then we could hear that little sound being transmitted. Something would change as we bridge the resistor across there. So, there we have it. And now what we've got to do is calculate how fast that pulse travels down the cable.